All right, so we're in section 5.4 today. We're going to do a couple days on 5.4. And we're talking about the sum and difference formulas. So just a new set of identities, really. The sum and difference formulas are on your sheet that I passed out the other day. They're on the side that says guidelines for verifying trig identities. They're at the bottom. They're handwritten in the bottom. So you all have these sum and difference formulas on that little half sheet. Does anyone need another half sheet? Would you like another one? And I'll have more of those if you need them. So the sum and difference formulas are just give us another way of working with trig functions. So what I'm going to do just to start is I'm just going to write the sum and difference formulas. You have them on your half sheet. I'm going to write them out and talk a little bit about the form, what they look like, and then we'll do a couple of examples of using them. So our sum and difference formulas. What we're talking about is if we have the sine of u, two angles added together, u plus v, and that is sine u, cosine v, and my v's and u's tend to look the same, so I put a little tail on the v. Sine u cosine v plus cosine u sine v. And sine of u minus v is the same thing, except we have a minus sign here. So we have sine u cosine v minus cosine u sine v. And then the formulas for cosine, similar, but with some important differences. So we have cosine of a sum u plus v is cosine u cosine v minus sine u sine v. And then we have our difference formula, u minus v, cosine u cosine v plus sine u sine v. And then we have a couple for tangent also. Tangent of u plus v. The formula is a little more complicated. Tangent u plus tangent v. And we divide that by 1 minus tangent u times tangent v. And our difference formula almost the same, just with some signs changed around. Tangent u minus tangent v over 1 plus tangent u tangent v. So when we do our quizzes, when we do our tests, you'll have this half sheet. Memorizing these, so you don't have to memorize these. I really don't have these memorized either. The ones that I would suggest, the identities that we worked with, the Pythagorean identities, it's good. It helps you out to have the Pythagorean identities memorized, and the reciprocal identities. Secant of theta is 1 over cosine theta, those. And I think we've worked with them enough that a lot of us do have those memorized. But these because there's so much going on with these, I really don't. I haven't memorized them, so I wouldn't expect that you guys would memorize them. The couple of important things that I want to point out just in terms of how these look are our sum and difference formulas for sine. The sine and cosine terms are mixed together. For the cosine, we have the cosines together and the sines together. For the sine formulas, the addition follows the addition in our parentheses here, and the cosine there the opposite. But the really important thing to remember, and this mistake is the kind of mistake that makes math teachers want to come back and haunt you guys after we die, is that the sine of u plus v is not sine of u plus sine v. The cosine of u plus v is not cosine u plus cosine v. And the tangent of u plus v is not tangent u plus tangent v. These don't work. These are like saying that x plus 3 squared is x squared plus 9. It doesn't work that way. It would be nice if it did, but it doesn't. Or this is like saying that the square root of x plus 1 is the square root of x plus 1. It doesn't work out that way. So don't make these mistakes. The formulas are more complicated. A big part of what we do with the sum and difference formulas is we need to match the pattern. So we're going to be given a problem, and we have to match the pattern of the identity. That's a big part of what we do with these sum and difference formulas. So any questions on the formulas? You have them on your half sheet. All I want to do now is just do a few examples of the kinds of problems you might see using these formulas. All right. So one of the big examples, big types of problems that you'll be given, or you have to do with sum and difference formulas. It will say something like, find the exact value of sine of 15 degrees. Now, these words, exact value, that's a hint. When we say exact value, we don't mean put it in your calculator and tell us what your calculator says. Exact value is a hint that you're going to be using your unit circle. So exact value means somehow we're using our unit circle. That's where our exact values, the exact values that we know, that's where the exact value comes from. So for this problem, problems like this, what we're doing is we want to find unit circle angles that add or subtract to get 15 degrees. So what two angles on the unit circle do we know that we can add or subtract to each other, from each other, to get 15 degrees? – 30 and 45. 30 degrees is 45 degrees minus, I'm sorry, 15 degrees. 15 degrees is 45 degrees minus 30 degrees. So these are our two unit circle values. This exact value is a hint that we need to use our unit circle. So the sine of 15 degrees equals the sine of 45 degrees minus 30 degrees. And we have a nice identity for finding the sine of the difference of two angles. This is the sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees times the sine of 30 degrees. And we can find these values on our unit circle. The sine of 45 degrees is square root of 2 over 2. The cosine of 30 degrees, square root of 3 over 2. The cosine of 45 degrees is also square root of 2 over 2. And the sine of 30 degrees is 1/2. So we have the square root of 6 over 2 minus the square root of 2 over 2. Now we can't say that the square root of 6 minus the square root of 2 is square root of 4. It doesn't work that way. So we just write this as square root of 6 minus the square root of 2, and our common denominator is 2. Oh, and I messed up here. I didn't multiply correctly, did I? I multiply straight across, so this should be, my denominator should be 4. Yes, sine of 15 degrees is square root of 6 minus square root of 2 over 4. So that would be the exact value of the sine of 15 degrees. So that exact value, that's a hint that we need to figure out something from the unit circle. All right, let's look at another example. Any questions on this one? Now when our angles are in degrees, it's a little easier. When our angles are in radians, that makes it a little trickier. So for this example, we want to find the exact value of the cosine of 7 pi over 12. The word's exact value tells us that we're using the unit circle. We want to find two angles that add or subtract to 7 pi over 12, and we want these angles to be unit circle angles. So anybody have an idea of how we might do this? Well, we could, let's start out. We know that when we add or subtract, we have some kind of fraction. Let's start out with a common denominator of 12. So we're going to have something pi over 12, and we have a plus or a minus, and something else pi over 12. And we want these two to add to 7. Well, do we have fractions of pi over 12 on a unit circle? No. So we want fractions that either with a 2 in the denominator, a 3 in the denominator, or a 6 in the denominator, right? We have pi over 2, we have pi over 3, we have pi over 6, we have those angles. So what two numbers could we add or subtract here that when we put them over 12 would give us, we also have pi over 4 on the unit circle, would give us those fractions. Anybody have an idea? Yeah.
7 pi over 6 and 7 pi over 4.
Well, and I want my numerators to add to 7. So I'm going to add these two fractions. So whatever I have here, plus or minus whatever I have here, is going to add to 7. Yeah. Now remember, when we add fractions, we're kind of on the right track. When we add fractions, we add the numbers in the numerator, and we keep our common denominator. So two numbers that are going to add to 7 that are on our unit circle as a numerator. How about 3 and 4? 3 pi over 12 plus 4 pi over 12. That equals 7 pi over 12. And 3 pi over 12 is what if we reduce it?
Pi over 4.
Pi over 4 plus pi over, and we need to, when we reduce this, we're going to divide, what's that? Pi over 3. Pi over 4 plus pi over 3 equals 7 pi over 12. So the cosine, after that little bit of work, we get the cosine of 7 pi over 12 equals the cosine of pi over 4 plus pi over 3. And we have a nice identity for the sum of the cosine of the sum of two angles. This equals, we look at our identity, cosine of pi over 4 times the cosine of pi over 3 minus the sine of pi over 4 times the sine of pi over 3. So I'm just plugging these values into my identity, and then I can look these numbers up on my unit circle. So this is 1/2, or I'm sorry, square root of 2 over 2 times 1/2. Cosine of pi over 3 is 1/2 minus the sine of pi over 4 is square root of 2 over 2, and the sine of pi over 3 is square root of 3 over 2. And I'll multiply my fractions correctly this time. This is square root of 2 over 4 minus the square root of 6 over 4. When I multiply radicals, I can multiply the numbers inside. So my exact value then would be the cosine of 7 pi over 12 equals square root of 2 minus square root of 6 over 4. That would be our exact value of the cosine of 7 pi over 12 using our identities. So when it says exact value, we need to find two unit circle angles that add or subtract to give us the angle that we're interested in. Questions on that one? All right, let's look at an example going the other direction. So rather than putting the angles, taking the angles apart, we're going to put them together. So for this example, we want to find the exact value of this long expression, cosine of 78 degrees times the cosine of 18 degrees plus the sine of 78 degrees times the cosine of 18 degrees. So when we see problems like this where we have these sines and cosines mixed together, our goal here is to match the form of our problem to one of our identities. So we want to match the form of this problem to one of our identities. We have the cosines together and we have the sines together. So this, if we look on our sheet, this matches the cosine of the difference of two angles. Our identity says the cosine of u minus v This is supposed to be a sine, yes. Thank you. It wouldn't work otherwise, would it? Thank you, son. So cosine of u minus b is cosine u cosine b minus sine u sine b. So this form matches this identity. So here u is 78 and b is 18. So we're going to go from here to here. Yeah, Kevin. This should be plus, yes. Thank you. Little details like that often get lost when you have a cold. All right. And you can believe that it's a cold or just because I forgot. Either way, works for me. So we match this form, so we're going to say this is the cosine of 78 degrees minus 18 degrees, which is the cosine of 60 degrees. And we look on our unit circle, the cosine of 60 degrees is 1/2. That's all we have to do. So when we have a problem where when we have angles and sines and cosines mixed together like this, we look for the identity that matches the form of our problem and see if we can use that identity to help us out. The exact value is a hint that you're going to be finding your answer on the unit circle. So we have to end up with some kind of unit circle angle that we know. So that's our hint that we're going to end up with some angle, pi over 3, pi over 4, pi over 6, pi over 2, one of those angles, 30, 60, 90, 45. So we're going to end up with one of those angles so we can find the exact value. Questions on that one? All right, let's look at one example with the tangent formula. And then we'll be done. So we're going to use one of our tangent identity. So we want to find the exact value. Exact value code for on the unit circle. Exact value of tangent of 255 degrees. So because we see this code that says exact value that tells us we're on the unit circle, we want 2 unit circle angles that add or subtract. To 255 degrees. So what are 2 angles that would add or subtract? And there are more than one way that you can do this. You get the same answer no matter how you do it. So what would be 2 unit circle angles that would add or subtract to 255 degrees? Anybody have a suggestion? I'm going to say 300 minus 45. 300's on our unit circle. That is 5 pi over 3. And 45 degrees is for sure on our unit circle. So the tangent of 255 degrees is the tangent of 300 degrees minus 45 degrees. And we have a nice formula for the tangent of the difference of 2 angles. And I'm just going to plug my angles in there. That's the tangent of 300 degrees minus the tangent of 45 degrees. And we're going to divide that by 1 plus tangent of 300 degrees times the tangent of 45 degrees. That's what our identity tells us that this is. Now we can look up the tangent of 300 and the tangent of 45. This is negative square root of 3 minus 1 over 1 plus negative square root of 3 times 1. So we get, I'm going to rewrite this in a more standard form, minus 1 minus the square root of 3 over 1 minus the square root of 3. Now, if you had a problem like this and you got to here, that would be, you would get the vast majority, on a quiz or test, you get the vast majority of points. Does anybody, normally we don't have a radical in the denominator. Does anybody remember how we rationalize denominators like this? Well, normally if we just have a fraction like 1 over the square root of 3, we multiply the numerator and denominator by square root of 3 over square root of 3. Well, if I multiply the denominator by square root of 3, that would get rid of this radical, but then I would be multiplying the 1 by the square root of 3, and I'd still end up with a square root of 3. Does anybody remember the trick? We used something like that when we worked a couple of identities. What we do, not almost, we're getting closer. I'm going to multiply, and the hint that I gave for the trig identities is it's almost like with complex numbers where you multiply by the conjugate. I'm going to multiply the numerator and denominator by 1 plus the square root of 3 over 1 plus the square root of 3. So I just change the sign here and multiply the numerator and denominator by that. And then I have to FOIL each of these out. In the numerator, my first is negative 1. My outside is minus square root of 3. My inside is minus square root of 3. And my last is negative square root of 3 times square root of 3 is just 3. And on the denominator, my first is 1. My outside is plus square root of 3. My inside is minus square root of 3, so the square roots of 3 add up to 0. And my last is minus and square root of 3, and the square root of 3 is just 3. And when I simplify this, I get negative 4 plus 2 square root of 3. Negative 1 plus negative 3 is negative 4. Negative square root of 3 minus square root of 3 is, and this should be, this should be a minus. Negative 4 minus 2 square root of 3. Minus square root of 3 minus square root of 3 is minus 2 square root of 3. Divided by 1 minus 3 is negative 2. And I can simplify just a little more. Negative 4 divided by negative 2 is a positive 2. And negative 2 divided by negative 2 is plus 1. And I just get 2 plus square root of 3. And I think what I did on quizzes and tests last year was, if this were a 4-point problem, getting here would be 3.5 points, and rationalizing your denominator would be a 0.5 point. I think that's what I did last year. It's the important thing is that you know how to use the identity and get to here. So, exact value, that's a clue that you're looking for something on the unit circle. And if we have something that's mixed, sines and cosines mixed together, we're matching the form of our problem to one of our identities. That's really the two approaches that we have with these sum of difference formulas. Questions on using these formulas? On Monday, we will talk about using the formulas to solve equations, and also to actually to prove a couple of identities. But, so Monday we're going to do just a little bit more of the sum and difference formulas. All right, so our homework for today. Now that's what I like to hear. Yeah, go ahead. All right, there you go.